I want to show you guys. It's not on. While I was at the ACS conference, I listened to a speaker talk about this website that he had curated with endless OChem practice problems. I found out actually he has endless GenChem problems on there as well. So under your external resources, if you scroll towards the bottom, it says endless practice problems. They are AI guided, so take some of them with a grain of salt. Some of these feel very OChem 1 heavy. Some of them are definitely OChem 2. And it's really not like a course-wide resource pool. Like you can't find everything from every chapter. But a lot of the fundamentals are here. For instance, functional group identification. If you are someone that needs more practice with functional groups, please use this. Every single problem that I've gone through has been very good at being correct about functional groups. One thing that I struggled with was their comparing resonance contribution. This is a good example, actually, because obviously one of these maximizes formal charge. So the one with minimum formal charge is a better contributor. But then they'll give me structures. This one does the same, it's just maximum charge, maximum charge. Okay, I think this is a good one for us to go through because if you follow my rules for resonance, you might answer this one the same as me, and we'll test whether it actually gives what it should. Anybody want to talk us through this? Which of these resonance forms is more significant? Which is more stable? There's a minus here and a positive here. Positive and minus.
The right one should be the major.
Right structure is major?
Yeah, you don't want a positive charge on oxygen. You'd rather have a positive charge on carbon.
Okay, so Elliot is saying charge placement. Place the positive on carbon rather than on oxygen. Milena? So Milena says maximum octets satisfied here. Maximum octets are not satisfied here. And my list for you has always been number 1, minimum charge. Number 2, maximum octets. Then place the charge appropriately. So it is more appropriate to have a positive on a less electronegative atom unless that means we are minimizing octets. So my rules for you would have said A is a better contributor. Let's see what they say. Oh, that's really reassuring. I did so many practice problems because I think this is really an interesting, that's a challenging one. What? Oh. Maybe they're equal to each other. There's an option for them to be equal contributors. Oh. That would be a very niche question. I can't imagine what rule they were getting from there. But there were a lot of problems that I saw that, of course, today won't show up, that were showing like very much the opposite of what I would have picked. And they looked a lot like the intermediates during our EAS and NAS reactions. And I could not figure out what rule they were basing this on. So anyways, a grain of salt when you're doing the resonance contribution. They have arrows, and actually the arrow pushing is very unique. I kind of like it. You draw on one structure what needs to be done to form the next structure. It has these spots where it lets you draw from and end at, and you can erase them just by clicking on them. You can draw an arrow anywhere you want to and have any kind of crazy shape that you want, and as long as you end at a certain spot, it cleans it up for you. So I would say it's a good practice resource. Nothing is as good of practice as doing pen to paper. Having pen to paper is a very important skill, because when you get to the final and you need to show things pen to paper, you don't want AI to just autocorrect it for you. And it also has mechanism arrows, but some of these are OChem 2, some of them are OChem 1. One thing that I do not like about these mechanism arrows, do you think you guys can figure out what I would take points off for on this? Thank you. No lone pair. It looks like it starts at the chlorine, but that symbol for chlorine is representing the nucleus of chlorine, not the electron shell of chlorine. And it's the electrons that are responsible here for forming the bond. So I'm not a big fan of that feature alone, that it doesn't ask you for the chlorines. Maybe that means that other people out there really don't care about the relevance of lone pairs. And they're like, oh, you knew the electrons came from that atom. But I have watched a lot of students learn, and I can tell you for a fact, a lot of students don't know that that arrow is coming from electrons. They probably think that it's coming from the atom, because they're not considering what is going on. So that's why I do enforce lone pairs being shown. I want you to be forced into an understanding of it. Okay, cool website. And if you're someone studying for the MCAT or the DAT or any other entrance exam on chemistry, take advantage of their Gen Chem practice too. It's a lot of good resources on here. All right, last class we were discussing aldol addition and aldol condensation reactions. And we said that we can take the same starting material, two equivalences of a carbonyl. What carbonyls are allowed in aldol reactions? Ketones and aldehydes. That's it. If it's aldol, it's ketone and aldehyde. And we said we can take two equivalences of these, and we can mix them together. Oops. And we can get an aldol addition. What functional group results from aldol addition? Okay, a ketone and an alcohol with a specific structural relationship consistently. Beta hydroxy carbonyl. Good. I didn't move my thing back. So beta hydroxy carbonyl, if they run addition, and I want to clarify, we've been doing a lot of acyl addition this semester. This is just acyl addition. A nucleophile, the same color. A nucleophile attacked an electrophile, and that electrophile was a carbonyl carbon. The nucleophiles we've seen earlier in the semester were Grignards, nitriles, alcohols, amides, water, doing acyl addition. Even reducing agents like NaBH4, sodium borohydride, LiAlH4, LaH, lithium aluminum hydride. We're going to look at that mechanism. That'll be a mechanism that you may have to show on the final exam. But then we said, if I have two carbonyl compounds in the reaction together, I can get a crossed aldol reaction. Carbonyl A might become a nucleophile and attack carbonyl A. Carbonyl A might become a nucleophile and attack carbonyl B. Carbonyl B might become a nucleophile and attack carbonyl A or attack carbonyl B. So in addition to the idea that we could do addition or elimination, and this is something that I will clarify what I'm looking for from you because the reagents are the same. In addition to doing addition and condensation, oh, and the functional group from condensation? A ketone. A conjugated carbonyl. It's conjugated through alpha and beta. So alpha beta unsaturated carbonyl, conjugated carbonyl, either of those would work. It's not just that there's a carbonyl and an alkene, but their structural relationship to each other is important there. So we devised some rules that we can use to limit crossed aldol products. Our first rule was limit alpha hydrogen positions. If only one of my carbonyls can become a nucleophile, then I have much fewer crossed products to have to deal with. Our second rule was selective reactivity. Make one carbonyl far more reactive. And if you can, do both. Like cyclohexanone reacting with formaldehyde. There's only one position that can become a nucleophile. And formaldehyde is by far a better electrophile than cyclohexanone. So when a molecule of cyclohexanone becomes a nucleophile, will it more easily attack a molecule of formaldehyde or attack another molecule of cyclohexanone? Selective reactivity says it's more likely to attack the more reactive electrophile. This takes less energy, so it's going to happen sooner. But it's not zero. There's still a non-zero chance that a nucleophile will form from one molecule of cyclohexanone and attack another molecule of cyclohexanone. So I still can get crossed products. Just maybe smaller. I just realized I didn't give you the addition product from cyclohexanone and formaldehyde. Let's do a little pop quiz. Can you draw the beta hydroxy aldol addition product that forms from this reaction? What patterns can you recognize from the example in blue that you can copy and paste into a new molecule with formaldehyde? What would the aldol addition product look like? Close. But that is not a beta hydroxy carbonyl, is it? Man, they changed the ingredients in my protein shake. I can taste it. I don't know. spicier.
That thing?
Do you want to explain it to Max?
So when, yeah, I guess on this sheet, when you react, what is
You want a beta hydroxy version of this product?
Yep.
A beta hydroxy, okay.
Yep. A beta hydroxy product of cyclohexanone with formaldehyde. What would the beta where is the beta position? What would it look like for a hydroxy group to be on it? Close, but that is alpha hydroxy.
It's supposed to be beta.
Should be. That's the rule. So when these come together through condensation, alpha beta unsaturated, when these come together by addition, what does the addition product look like? That is its beta position. But remember, do you remember the OChem?
You're not wrong.
Did you watch the video from Tuesday?
No.
Oh,
I'm just fine. I didn't watch the end of the video.
we established some OChem lore.
Lore? Was I here for this?
I
though?
think so,
Okay.
yeah. What's the secret password? Oh, I found out it's not this.
Was it beta hydrogen? Was that it? Alpha carbon? I don't remember.
It's, does anyone speak sign language? ASL?
Yeah, but what is this? I thought it was like be quiet or something.
8. Like 6, 7, 8, 9.
Oh. 8.
She ate that. Clocked it. Clocked 8.
I'm like, that's not 8. This is 8.
But that's
so let me
eat.
hold up 8 really quick.
Yeah. Did you get it?
I don't know, did I? Is that
Oh yeah,
right?
that is. Bro. What?
Wait. Yeah?
Yeah.
Where is it?
So then you said what I did was wrong.
Okay,
Because
so
I'm
what's the
missing a
T?
part?
Yeah.
I don't know.
Yeah.
So
Beta was a carbonyl carbon.
I forgot. That was a password. I'm all. Is beta hydrogen alpha carbon?
That beta position got attacked by the alpha position. And the carbon that gets attacked is a carbonyl carbon. So the new products, beta hydroxy, alpha beta unsaturated, beta was a carbonyl carbon. That's where it came from. So you gave me a good answer, which was here is a beta hydroxy carbonyl. But that is the original compound's beta position. Beta was a carbonyl carbon. So the addition product that I was looking for here is when alpha attacks beta, acyl addition. Alpha attacks beta, acyl addition.
Okay, that
I
was
know.
my second choice. No, it's okay.
Very slow. I've been going slow.
It's okay. That was literally my first choice. Okay, slow too, so it's okay. It's just better for me.
Good.
I haven't been able to do any OChem homework in like 2 weeks because I was prepping for an exam that I just took, and now I get to, and I'm so excited.
Good. I'm glad to hear that. Do your homework and have fun.
She's excited to take your final. Oh no, no.
All right, here's our beta hydroxycarbonyl. Agree, disagree, complaints, concerns, critiques?
I'm just confused as to like what, so it's NaOH is doing the substitution,
NaOH is catalyzing
the substitution,
the reaction.
but you're combining it with the what is it called? Aldehyde?
Aldol.
Aldol.
Yeah, okay, so when you rewatch Tuesday's episode, you'll learn that we call it aldol because if this is an aldehyde, it forms an aldehyde alcohol compound, aldol. But it can apply to ketones too.
Oh, so it's just undoing it and making it into a hydroxy group.
It's actually doing acyl addition. So it's forming a carbon-carbon bond, breaking the CO bond.
Okay, that actually makes sense. I get it.
Rule number 3. These rules work, but they don't completely minimize side products. So rule number 3 for a good synthesis with aldol reactions is to lean into complete enolization. In order to understand this idea of complete enolization, I want to take you guys back to some of the bases that we have considered. If I have acetaldehyde and I react it with, 2-butanone. I need some regio distinction here. If I react this with NaOH, I get the, let's keep the pop quiz going. Is NaOH a kinetic base or a thermodynamic base? Will NaOH form a kinetic enolate or a thermodynamic enolate?
When did we talk about this? Can you go back?
NaOH is a small base, so it can overcome those large activation barriers in order to form the more stable enolates. So NaOH is a thermodynamic base. How well can it do this? Well, the byproduct of that step, the conjugate acid, is water. And we've already discussed pKa's. This has a pKa around 20, and this has a pKa around 15.6, depending on who you ask. So which side of equilibrium is favored? Does the enolate form well, or does the ketone stay formed well? Right. Worse acid, better acid. Better acids do their job. They act as acids. So whichever side has the better acid is not sticking around. So my equilibrium favors the formation of the ketone. At any given time, we have less than 1% enolization, which means we have greater than 99% carbonyl. In the world where the enolate is a nucleophile and the carbonyl is an electrophile, this is telling me that for every nucleophile I actually form, there's 99 other electrophiles for it to interact with. So in terms of trying to mitigate cross-aldol reactions, it's swimming in a world of all other carbonyls, all other electrophiles. 1% enolization, not great here. In fact, I want to say maybe more, like 10%, still not great. If we run something similar with tert butoxide, really the only distinction is what type of enolate is formed. But because tert butoxide is an alcohol, water is just an inorganic alcohol. Their pKa's are very similar. This gives us about 1% enolization. If you guys remember Le Chatelier's principle, I form 1% enolate, but then that enolate reacts. I no longer have that 1% enolate, so now I can form more. So as the enolate forms, it reacts with a carbonyl that's left behind. There's a lot of them. But now there's no enolate left, so it's allowed to, or a new enolate is formed. So the equilibrium shifts forward as I remove those enolates by reactivity. So they will react. They do all the reactions we're looking for. They just do it very slowly and uncontrollably because everything is present. So the idea of complete enolization is to use LDA. LDA, and we can write this separate. Yeah, we're coming back to it finally. LDA is lithium diisopropyl amide. Do you see an amide there? You do. Amide is the name of the negatively charged nitrogen. I know. It's a bad name because amide is also the carbonyl bonded to nitrogen. When this reacts, what type of carbon is it going to go for? The less substituted or the more substituted? Yeah, it's big and bulky, so it doesn't want to put up with the steric strain. It can't put up with the steric strain. It takes the most accessible hydrogen, gives us our thermodynamic enolate, but it also gives us an amine. Once again, pKa around 20, but now my conjugate acid has a pKa. Any idea? Where is the pKa of an amine? We covered it in OChem 1. We took advantage of the pKa of amines to deprotonate alkynes. Opposite, it's pretty basic. And it's not a good acid. This has a pKa in the 30s. If it were, we use like a similar type of base like this to deprotonate an alkyne, because the conjugate acid here is less acidic than an alkyne.
Oh, that means it's a good base, right?
Yeah, so this is a good base to take our alkyne hydrogen. Now which side of equilibrium is favored? The products. Now we've got essentially greater than 99% enolate and less than, that's not a greater than symbol, is it? Is greater than 99% complete? Because that's what I was going for, complete enolization. No, not really. So maybe it just looks better, or yeah, just call it 100%. And that's essentially how it will behave. It is such a good force on equilibrium that we essentially have no carbonyl left over. And we are at 100% enolization, which means carbonyl A doesn't exist anymore. So the nucleophile can't attack carbonyl A. This is a great synthetic strategy. It is limited on one front. Aldehydes and esters only have one alpha hydrogen position at the most. So LDA forms 100% enolate of aldehydes and esters, and there's never a question about what that enolate looks like. But some ketones have both a thermodynamic and a kinetic enolate, and LDA is limited to the kinetic enolate. So there is a bit of a regioselective issue. If I wanted my nucleophile from a ketone to attack more substituted, I wouldn't really be able to take advantage of complete enolization. I'd have to factor in my other two rules. But if I have a ketone where it doesn't matter which side I pick, there's not a kinetic versus a thermodynamic side, then complete enolization works every time. Aldehydes, esters, and symmetric ketones. So let's show a few problems, shall we? Actually, what does the sheet have? Just one? Oh, right.
Do you have an extra one of those sheets too?
I sure do. So I would like you guys to use LDA in step 1, and then decide for yourselves what second carbonyl do you want to introduce in the second step. You'll form an enolate with the carbonyl that's already given. And then you pick a second carbonyl to introduce. I want to see the aldol addition product from the structure that you chose. I want to see the aldol elimination, aldol condensation product from the structure that you chose.
So step 1 is the L what?
Step 1 is LDA. Introduce your carbonyl and completely enolize it.
And 2 is whatever carbonyl we want.
Yeah, so remember earlier we were just showing mix 2 carbonyls with a catalytic base. Now we're saying mix 1 carbonyl with LDA, and after that has been formed, introduce it to a second carbonyl. Gets to be whatever you want.
So in the orange is after LDA, right?
Here? Well, this is just the enolate that forms
From LDA?
from LDA. I mean, it's the same enolate that forms from tert butoxide.
Oh, yeah.
This is the enolate that forms from LDA. There is a similar enolate that forms here when we're forming these structures. And it's the enolate, we'll look at the mechanism next. It's the enolate that attacks from the alpha position and gives
I remember.
aldol addition.
So you said add a carbonyl after?
Right, so instead of mixing 2 carbonyls at once and hoping that we only form 1 enolate and attack 1 carbonyl, we're not taking the risk of getting these side products anymore.
Oh, using LDA, you just get the product that you want.
Yep. I'll try to say this. Let me demonstrate it better. Once again, starting with cyclohexanone and formaldehyde and NaOH. How many of these molecules might I have in a reaction if I'm running upstairs to run this? A lot, like hundreds of billions of molecules. So imagine hundreds of billions of molecules. For right now, I'll just draw a couple of the equivalences that would be swimming around in my reaction. When NaOH comes in, it forms an enolate from one of those hundreds of billions of molecules. Now that enolate wants to act as a nucleophile. Where can it act as a nucleophile? It could attack the carbonyl here, could attack the carbonyl here. Those would give the same product. It could attack the carbonyl here. Oh, that would give a different product. Thus, my selective reactivity, this would take more energy to attack. Ketones are less electrophilic. These would take less energy to attack, so it's more likely that it attacks here, but it's a non-zero chance that it attacks here. I don't want to do that. So I'm going to take, what compound did I give you? Great. I'm going to take 3-phenyl propanal, and I'm going to react it first with LDA, which is going to give me the enolate of 3-phenyl propanal. 100% of my molecules become that enolate. They will not attack each other because there are no carbonyl versions left of them. Now I introduce what carbonyl I want to attack. This is your decision. Pick an aldehyde, pick a ketone. Maybe take advantage of what's already on the board. Maybe take advantage of some versions we used last class. I think Indigo's going with benzaldehyde.
Why does it not form this enolate?
There is no alpha hydrogen there. There's no carbon there. And then think about your patterns. What will the beta hydroxycarbonyl look like? What will the alpha beta unsaturated carbonyl look like? That's the aldol addition and the aldol condensation product. You already know where alpha is. Alpha is coming from that aldehyde that we started with. That's the nucleophile. Beta was a carbonyl carbon. So whatever carbonyl you introduce, now you know what beta looks like. So what do you want to introduce? Ditert-butyl ketone, acetone, acetaldehyde, benzaldehyde, acetophenone, 2-butanone,
Can it just be anything though?
2-pentanone,
Well, I just
cyclohexanone,
picked an aldehyde.
3-methylcyclohexanone.
I picked an aldehyde. Is that
You
okay?
picked acetaldehyde. That's great. A world of options.
Huh?
Very close. That methyl group doesn't exist.
Which one? This one?
That methyl.
Oh yeah, you're right. But
Brilliant.
now it exists?
Yep. There's your alpha beta unsaturated product.
I was like, I did it like before you put that stuff on the board, and I was like, oh, that's wrong. And then I was like, I think I know the mechanism for this
I bet you could. It's not that hard.
because I'm saying OChem 1, but I can't remember what the mechanism.
Well, it's not an OChem 1 mechanism. It's an OChem 2 mechanism.
But does the negative jump down to create a double bond for the oxygen, and then that carbon's left open, like with a positive charge?
No. When this comes down to form the double bond, this electron has to move.
Breaks.
And it breaks to this carbon. So
Beta.
this carbon uses it. That's alpha. Carbonyl, alpha, beta. Alpha gets the electrons and attacks something else.
Yes.
Good.
I think I just have not your vocabulary.
Get on board with my vocabulary.
I can't.
You need to.
One day.
Huh?
Maybe.
Oh, yeah, after you watch one day, for sure.
Yeah.
And last week Tuesday, not Monday. Last week Tuesday I talked about the anatomy of the carbonyl. Did you watch that video?
You were here. I was here on Tuesday. I wasn't
Oh.
here on Thursday.
Yeah, carbonyl, alpha, beta. That's our vocabulary. Or our anatomy. Okay. Alpha attacks. Alpha gets the electrons. This is not alpha beta. This is alpha beta. This is actually carbonyl alpha.
Carbon off of the carbonyl. It's not that carbonyl carbon.
Correct. Peyton went with cyclohexanone as the second compound to introduce. Yvonne's going with acetone, which is great. I'm not sure if that's what you meant. That would work good. Use it.
I haven't watched the recording.
I see. Do you know what a beta hydroxycarbonyl should look like? Here's an example. Oh no, I erased it. Oh no, I got it. Here's beta hydroxy. Carbonyl, alpha, beta. Beta was a carbonyl carbon. I formed an alpha beta bond in doing this. So when you're looking for your product, just connect alpha to whatever your second carbonyl was. That's now beta. Put a hydroxyl group on beta. You'll have a carbonyl. So you can actually start by taking that aldehyde we're starting with and redrawing it. That aldehyde we started with will be in the final product. as an aldehyde, as a CO double bond. Great.
Yeah.
Absolutely. Yep. Carboxylic acid.
Wouldn't that create?
Both sides.
So this structure turns in
To that, right?
kind of, except there should be a double bond here.
Oh, I was missing that. You're right. Thank you.
And then it reforms this, but attacks from alpha and forms a new bond to a new beta.
You said because if this is the beta carbon, right?
Yep, it will become the beta carbon.
Does it? Okay.
What are you thinking?
I don't know.
Haven't picked a carbonyl yet.
Okay, these are really confusing. Is that like because that's our alpha,
Yep,
and alpha attacks the beta.
good.
But I don't.
Beta has a methyl group coming off.
Yeah.
Where did beta's methyl group go?
Well, I put it right there, but that's I feel like not correct.
Well, that's alpha though, or that is beta. That carbon is beta. And
Oh, right, yeah.
good,
Okay.
perfect.
I hate this. Okay. Yeah. Cool.
You can see why we save it for the end, right?
We should just not do it. Okay.
So Max, you got to start by picking a carbonyl.
Yeah, I'm just trying to figure out how this reaction works. I don't know how it works.
Don't worry about how it works. Just pick a carbonyl first.
I like looking at this. It's like, what's an enol? Like, it's the carbonyl to the alpha, which I don't understand. Because all these up here are like alpha, beta having become.
That's right. These are the products. This is the intermediate on the way.
Oh, that's the intermediate.
Yep. Alpha should form the bonds.
Does it keep the pH though? The phenol?
Yeah, although that should have a ring in it to be phenyl. It will. When alpha bonds to beta, then beta will be connected to pH. You have started with your carbon chain, but then you kind of turned this beta carbon, which was already present, into the aldol, or the alcohol. But that beta carbon's not undergoing any change. This alpha is going to bond to a new beta. We will increase our beta count. Good work. Okay, I think your alcohol is on the wrong carbon. So here's alpha.
But this is kind of backwards.
I think it is backwards. You're right.
Yeah, I kind of wrote it backwards. Yeah.
I think you have this guy attacking this guy. But this is being turned into a nucleophile first, then attacking this.
Okay.
So this alpha will bond to this beta.
Yeah.
Yep. All right, should we go over it? What carbonyl should we use? World of possibilities. Do you want something challenging or easy?
Challenging. Oh, I don't even know how mine works. I picked the basic thing.
You picked acid aldehyde?
Yeah, literally.
All right, the short and sweet of the mechanism is at step 2, I'm adding my second carbonyl directly to this enolate. It's this carbonyl doesn't exist anymore because after reacting with LDA, it's just this enolate. This enolate attacks from its alpha position. If it forms a new bond, that means alpha is bonding to a new beta position. Okay, I'm going to draw the final product. I'm going to sneeze. Oh no, I've never sneezed on the microphone before. I'm scared. Alpha bonds to beta, alpha to beta. Beta will now have an OH group. Beta has a methyl group. There is my alpha beta sorry, there's my beta hydroxycarbonyl.
Oh, I did it backwards. That's funny.
If you chose benzaldehyde, you don't have a methyl group. You just have a benzene. If you chose benzophenone, then you've just got a second benzene coming off of that position. Milena? We are. We are skipping a protonation step. Good eye. We're going to go through the mechanism after this. Aldol addition. I've done acyl addition. My aldol condensation product takes the alpha position of my carbonyl and the beta hydroxy group and eliminates them. Dehydration reaction condenses out water from the molecule. Once again, this is what it looks like if what you started with was acetaldehyde. Beta, you're not going to believe this, was a carbonyl carbon back in the day. How time changes things, you know. Oh man, I saw a really cool visualization of the different rates at which things move. Like cells can move in the course of seconds. Molecules can migrate over the course of milliseconds. Bonds, man, I wonder if I can find it. Bonds change over the course of nanoseconds. Chemical reactions happen in femtoseconds, and bonds vibrate in, no, maybe I've got that wrong. Chemical reactions happen in nanoseconds, bonds vibrate in femtoseconds. It's like to the scale of a bond and how quickly those atoms are compressing and expanding relative to each other. Like they do that so many times a second that by the time a chemical reaction has passed, they've lived entire lifetimes for us. What would feel like lifetimes to them. If atoms are conscious, it's a whole different experience. Just going to leave you at that. Okay, was that confusing enough? What do you think? Good stuff. Let's flip over to the second page and let's do the mechanism for aldol condensation. I think it's clear that you guys are curious about the mechanism. So let's look at the mechanism better. And then we'll come back and look at the Claisen and Dykman and crossed Claisen. Can someone name the starting materials? What's our starting material for this aldol condensation mechanism? 2-butanone. Perfect. Ella, what's missing from my worksheet? True. NaOH needs to go over the arrow. How do you know it's NaOH and not tert butoxide? We're looking at the mechanism on the third page. Did what? Really?
Down here only has 2 pages.
When did you download this?
On Tuesday.
Uh-oh. Did I not upload? I thought I uploaded it.
They might be 2 separate ones, and I just haven't looked. But
No, they were, I modified them to be one document. 2-butanone. And Peyton says, I need NaOH. Can I use terbutoxide instead? Why not?
You get a less substituted alkene.
You're right, Ella. I did not combine them. So you'll just,
It's on there though? That's
it's the next file. Michael addition condensation mechanisms. All right, correct. If I used a bulky base, I would get a less substituted nucleophile. I know that this reaction has reacted by alpha being a nucleophile, so I must use a kinetic base. Sodium hydroxide works, sodium methoxide, sodium ethoxide. Any of those small bases will be fine, but since I'm not dealing with an ester, I can use hydroxide. If it were an ester, hydroxide is off the table. All right, first step of our mechanism. I call it formation of enolate. How else could you refer to this? Oh, sorry, Ella, one thing I forgot. 2x.
Oh.
I need two
What?
equivalences of 2-butanone in order to form this condensation product. I'm going to draw both equivalences of 2-butanone, even if they're not necessarily involved in the same steps. So I'm looking for the formation of the enolate. I could have called this acid-base. I could have called this deprotonation. Either one of those would have worked just fine. I am going to show the formation of the major resonance form. If you are not interested in showing the major resonance form for this mechanism, unlike EAS and NAS, for this mechanism, I will allow you to show the formation of the minor resonance form, since it is the resonance form responsible for the next step. And some students have told me over the years, showing this version helps them predict the reactivity better in the next step. So this is allowed. Step 2. God, I hope I called it acyl addition. Somebody tell me I did. Oh, yeah, bad name. It's true. It's a nucleophilic attack, but it's specifically a nucleophilic attack onto an acyl group. So my nucleophile attacks from the alpha position. Again, if you're looking at it from this resonance form, you can see it a little bit more clearly how it attacks from the alpha position. I think it's more interesting to look at the major resonance form, but I do understand in this mechanism it can be a little confusing to understand the arrows. Okay, I'll be honest, the intermediates are a little clunky to draw. So your bond lines are likely to get a little cumbersome. Well, I guess I didn't need to say that. If we have a deprotonation step somewhere, then it's likely that I need to follow with a protonation step. What's my base? What's my acid? Well, my acid should be the conjugate acid of my catalyst. My catalyst is sodium hydroxide. I haven't reformed my catalyst yet, which means it hasn't really served its role as a catalyst. So my acid is the neutral oxygen with a hydrogen. My base is the negatively charged oxygen. Water acts as an acid. What functional group have I just formed? Good. Well said. Beta hydroxy something. Beta hydroxyketone. A beta hydroxycarbonyl. So this is the product of what type of reaction? This is not the Aldol condensation. We have not talked about Claisen yet.
What was the other one? The
We're-
Michael one?
This is the Aldol addition product. You see that we're not done with the mechanism for aldol condensation, right? So it would be strange to be done with the product when we're not done with the mechanism. So I am just on my way to getting the aldol condensation product. I have another deprotonation step. How do I form an enolate here? I'll need to deprotonate. From where? Yeah, if I deprotonate the OH, would you agree that that just takes me back a step? Okay, so let's not deprotonate the OH, which technically is not an enolate. Yeah, an enolate has resonance with the carbonyl. So where do I deprotonate to make an enolate? Alpha hydrogens are surprisingly acidic. Oh, I've really leaned into that trademark. So I haven't shown it yet, but I need to draw the remaining alpha hydrogen. And again, more substituted alpha hydrogen because I have a thermodynamic base. Once again, if you want to show the resonance form where alpha carbon holds it, you can show that. But I am going to show this resonance form. We just formed water for the second time, but this time for good. That is our byproduct. That is our condensation product. Our condensed product. The reason we call it a condensation reaction. And for the final step, how do I get from this beta hydroxy enolate to an alpha beta unsaturated carbonyl? By the way, I need to regenerate my catalyst. What can I do? Hydroxy acts as a leaving group. If hydroxyl leaves, it gets kicked off as hydroxide. That's my catalyst, so I have regenerated my catalyst. If that's a leaving group, then my O minus falls back down to reform my CO double bond. That's going to pinch the octet at the carbonyl carbon, so the enolate pi bond moves down between alpha and beta. And now I have an alpha beta unsaturated carbonyl. Nope, what did I miss? Didn't leave the leaving group. If you're showing that from the less major resonance form, you have less arrows, for one. But I do want to say this reaction, when students try to predict it, when you're not following the steps, when you're not showing this as a 5-step mechanism, there are a lot of students that will deprotonate and eliminate at the same time. And it's not the craziest suggestion to take this hydrogen and just immediately form the pi bond and kick off hydroxide as a leaving group. Do you guys remember in OChem 1, how often was OH minus a good leaving group? How often did we kick off OH minus? Not once. This is the first time that you've ever seen a molecule kick off an OH group. It is not easy to do. In order to do it, we need this intermediate. This enolate takes on that extra negative charge, stabilizes it between carbon and oxygen, and only after that has formed is the molecule in a state where it can kick off hydroxide. So, common misstep here is combining these steps and showing E2 elimination of hydroxide. It's not E2 elimination. I think it's called ECB1. I don't like it. It's like elimination, conjugate base, first order, or something like that. Okay? Don't forget it, whatever that was. What do you think? Good. What you'll notice is we did not go over the mechanism with LDA. My expectations for having you show mechanisms on the exam is to do a true Aldol condensation, not a crossed Aldol condensation. So you won't need to worry about more than one carbonyl that could be deprotonated. You're going to take a carbonyl and have it react with itself. Okay. Didn't give you guys a break yet, so take 5 minutes, move around, get your blood flowing, and we'll talk about our condensation reactions with esters. Hello. Hello. What's up? What? What? You can say it.
What?
I don't sound like that. You want that to live on the internet forever?
No.
You've been seeing about what's been coming out in
I've been
in
like,
Utah
you
about.
funny juice today. Like, what are you talking about?
You lost me at funny juice, actually. I don't know what you said after that, or before it. I guess I was lost before it.
I'm also lost. I'm not either together.
Didn't Ella's dinner look really good?
It smelled really good. Sorry.
Mashed potato and corn. It was just missing gravy.
Chicken.
some chicken nuggets. Oh my goodness. That's what I got every day I could from my college cafeteria.
That was actually the first thing I've eaten today, so. So, I was like, it was really good.
What time did you wake up today?
10?
Oh, yeah, you should eat something before that. But I'm glad you got food in your system now so you can thrive in OChem
Oh, absolutely.
and do all your OChem homework.
It's tomorrow.
I really just have a question and I can't even remember it.
It's okay. It'll come back.
It's okay.
It'll come back.
Oh, I know. What, there's a girl in our OChem lab,
Okay.
and she's in this class too, but we haven't seen her the past few weeks.
Sure.
Everyone's really worried about her.
Oh, okay. Yeah.
Well, you just can't remember her name. She's cute. She's the one that was like, I wear something different every single day.
Oh, yeah.
Oh, yeah. I don't know. I haven't heard anything. I thought I saw her last week. No?
She hasn't been in our lab the past like 2 weeks.
Oh, shoot. You can reach out and message if you want to offer some support. I think you guys are able to message each other on Canvas.
Oh, I just couldn't remember her name.
Now you got it, right?
Bella? Bellin?
Mm-mm.
Bellin?
Yeah. Well, I think the last time was right before the drag show. That was April 3rd. So yeah, it would have been 2 weeks.
Yeah.
Hmm.
Just worried about my girl, you know? I don't really know her, but
It's a nice concern.
I don't know.
I can reach out too. I had a student that apologized to me once. I think it was in my OChem 1 semester this semester, my OChem 1 class. And they said, I'm so sorry I haven't been to class recently. And I was like, yeah, I knew that.
You're like, no, for sure.
I was like, how long has it been? And they're like, oh, a month. And I was like, oh, dang it. I don't know. Like, it's a free classroom. Come and go as you please.
Valid. It's just that our lab isn't.
Yes,
So
that's
that
true.
was why we were concerned.
That's
not
true.
necessarily like this class. That's all.
Yeah. No sé. Mishnah Arif.
We're like, it would be such an odd time to give up, especially on lab, because like you can pass
Yeah.
lab without passing
Yeah, I would almost.
class, unless
I
you
mean,
crash.
I don't like to presume anything, but it's more likely just tight schedules and like lots of stuff coming up at the end of the semester, you know.
I also feel that, but I do go to lab.
Okay, question.
Oh, darn it. I didn't take a picture of that. It's okay.
Yeah,
Video.
it's on YouTube. It's pretty good high quality too. Pretty good high quality. Would you rather learn the mechanism for the next type of reaction we're going to do first and then talk about the reactions, or look through the reactions on the page before this and then do the mechanisms? Yeah? Should I, going forward, I am always making changes, introduce mechanisms before I introduce broad reaction types? Imagine back in section 15, our first unit passed the review. We learned about aromatic substitution reactions. Not section 15, section 16.
No, I like the way you had it structured.
And I gave you guys the diagram of all the different substituents you could put on the aromatic ring, and then we talked about their mechanisms. Should I have maybe just introduced the mechanism first and then gone through all of those reactions?
No, not for that one, because it was like important that you understood the difference in like EAS and NAS and their substitution.
Right. Although Elliot's saying yes. I didn't do a great job with the resonance part of that mechanism.
I feel like a mix of showing like one, like there's so many reactions, but they're just permutations. Showing like one, you know, like look at this reaction, and like just like I don't know, like a little bit before the mechanism helps. But then, at least with this one, these ones make more sense with the mechanism. I feel.
Yeah, now it clicked a little bit more.
Like a little.
Yeah.
Rather than just being like, look at these reactions, they fit together. Like,
Sure.
but could be outvoted.
What?
Said I could be outvoted.
I like mechanisms first.
Oh, this is not a
because
democracy. It's okay.
when
You don't get a vote. You just get a voice.
So it is a.
No, I'm pretty sure I can scream all I want in my democracy. It doesn't mean I'll be heard.
Oh!
I was making a joke about the state of our democracy. Voice, you don't understand the word.
True.
Whatever.
Okay, yeah, maybe it's a case-by-case basis. Yeah, maybe this one I should have. We did the mechanisms for tautomerization. Maybe I should have, in that moment, kind of shown how during tautomerization something can happen where it acts as a nucleophile. Hey, look at all these new reactions that we can do. Aldol addition, aldol condensation, crossed aldol. Okay, then our next mechanism is Claisen condensation. True or false, there is a Claisen addition reaction.
false,
Nice.
because we didn't cover it.
Yeah, we didn't cover Claisen condensation either.
Well, but I'm saying I feel like we would have done addition first.
We didn't do the aldol addition mechanism, technically. We only did the aldol condensation.
But you said there was addition.
There is no Claisen addition mechanism. There is no Claisen addition reaction. Claisen reactions are analogous to aldol reactions. Aldol involves what carbonyls? No, I meant starting materials. Aldol involves ketones and aldehydes reacting with each other, and it produces beta hydroxycarbonyls, alpha beta unsaturated carbonyls. Claisen reactions involve esters, and they form beta keto esters, which is a type of beta carbonyl carbonyl.
Sorry, are we starting with the mechanism?
We are
Okay.
by majority voice, not vote. We're going to take esters and we're going to generate beta keto esters, or in some instances, beta aldehyde esters, and in one instance, beta ester esters. It's going to be great. It will be. All right, step one, very much similar. I need two equivalences of an ester, but I'm giving you an instance here where those two equivalences are attached to the same molecule. What base should I introduce in my reaction? Sorry, this is actually just going to be the overview. I will need a base to catalyze this. What base can I use? Only one base that I can use. I don't get choices with esters. One base. Sure. Methoxide. I need a base that matches my ester linkage. So I need Methoxide.
If it was another one, would it be ethoxide?
Correct. 2-carbon chain, ethoxide. Lily, is it okay if I use MEO- or CH3O-? Perfectly interchangeable. Yvonne, would you agree that the product shown is a beta keto ester? Here's ester, alpha. Hey, there's a ketone on beta.
Oh, that's what that means.
It's wild that beta keto ester means a ketone on the beta position relative to the ester, isn't it?
That's wonderful.
I didn't even come up with that.
Let's remember that.
They did that all on their own. Not the esters, the people in charge of stuff. Okay, step number 1. Deprotonation. Formation of the enolate. How many places do I have in this molecule that can be deprotonated? Okay, where is one? Deprotonate the carbonyl. I think historically there are no hydrogens on that carbon. Right. Okay, so you said 2 because there are 2 carbonyls, yeah?
Yeah.
But neither carbonyl has a hydrogen. Carbonyls that do have hydrogens are called aldehydes, and those hydrogens are not acidic. Did you say 2 as well? Were you also thinking the carbonyl carbon? Okay. Where did we deprotonate in the aldol condensation mechanism?
On the alpha carbon hydrogen.
Because alpha hydrogens are... That was great. Alpha hydrogens are surprisingly acidic, so methoxide deprotonates at the alpha position. Once again, you are welcome to draw the less major resonance form if it helps you understand the reactivity better. Why did I deprotonate that alpha hydrogen? I should have asked you guys if we should have taken the other carbonyl's alpha hydrogen. Indigo? Why did I deprotonate here from this alpha hydrogen rather than this carbonyl's alpha hydrogen? It has no alpha hydrogen, right? That alpha carbon has no hydrogen connected to it.
That dang circle's throwing me off.
Ah, see, I told you guys drawing a circle is bad.
I'm like, no, there is one there.
But it's so much easier. Oh, and when I'm in OChem 1 and I decide to give a reaction with an aromatic ring, and I'm like, I have to draw these bonds, this is crazy. Because I refuse to draw the circles until I explain aromaticity. It's my own fault. I'm crazy. You're just figuring that out. Instead of nucleophilic attack, what do I think you should call step 2? I made this, but yeah, acyl addition. Who attacks whom in this acyl addition step? Good. Alpha carbon attacks the carbonyl carbon. Did you know it doesn't matter how you draw your arrows here? You could circle them around the paper and then come back so long as they start and end at the right spots. So carbonyl reforms and alpha carbon attacks carbonyl carbon. That's going to generate a new beta carbon. Acyl addition. we know that this should form a 5-membered ring. Let's just check it. Alpha attacks beta. 1, 2, 3, 4, 5. Back to alpha. Great. 5-membered ring. Here is alpha. Alpha has just reformed its, I'm going to change my esters to say OME because I don't like drawing that little stick anymore. My ester has reformed up there. Alpha has just attacked beta. But beta was a carbonyl carbon. Yes, we've just done acyl addition, a tetrahedral intermediate. Now, this reminds us a little bit of our reactions in Unit 4 with esters, carboxylic acids, acid halides, amides. This tetrahedral intermediate has a good leaving group that it can kick off. Sorry, I don't want to go too fast. What am I calling this? There might be a better name for this than elimination. I just worry the name that I would give it doesn't make sense to you. I might call this tetrahedral collapse. The O negative collapses back down into a double bond, reforms the carbonyl. So my little tetrahedral is going to reform. I call that a tetrahedral collapse. But I don't know if that's the best word. For you, maybe you'll think elimination sounds good. Are you guys okay with the fact that I changed my ester mid-mechanism? I went from O line to OME. Because it would just, for me, it looked easier to draw. Carbonyl reforms, and my ester linkage gets kicked off as a leaving group. Oh, I've been forgetting something, haven't I? I'm sorry? Yeah. So way back when, methoxide deprotonated my alpha carbon and gave me a byproduct of methanol. That is what was condensed out of this reaction. First step, I've got my condensed molecule of alcohol, which means I never recouped my, I'm trying to say it, but my brain is lagging, never recouped my catalyst. My catalyst is still lost. But here, when I kick off my ester linkage, I reform my catalyst. Sorry, so that doesn't need to go in parentheses. Looks like we're done, right? Isn't that the product? Methoxide is not on the final product. That is.
Oh, I'm like looking, I'm like, yeah, this, no. Sorry.
Doesn't that look like the final product? Yeah. Beta keto ester, 5-membered ring formed. How many more steps in the mechanism? There's 2 more on the sheet. Oh, I think you're off by a step. No, I get it. You formed this.
Yeah.
Next step says form the enolate again. Hello, I'm done. Why would another enolate form? Where would an enolate form? No, that's a good question. Here's an enolate. An ene, all, negatively charged.
Okay.
The enolate is the conjugate base of the alpha hydrogen elimination, deprotonation. Why would an enolate form after this? We still have an alpha hydrogen, but it's not the same alpha hydrogen. It's not in the same conditions that we had before. Would you agree that this is the alpha hydrogen of an ester, but this is a shared alpha hydrogen of a ketone and ester? Which one is more acidic? Yeah, the shared alpha hydrogen is far more acidic, like more than 10 orders of magnitude more acidic. So if I was lucky enough for my methoxide to deprotonate this alpha hydrogen, pKa 25, 1% enolization, 0.1% enolization, and lucky enough for that enolate to form, run acyl addition, and then collapse back into the beta keto ester, I have now made the second alpha hydrogen 10 billion times more acidic. So in the presence of that catalytic base, my alpha hydrogen gets deprotonated. So I reform my enolate. And then what? I had the structure that I wanted, and now I don't have the structure that I want. Oh, I can't do that right, can I? Do you agree there are two major resonance forms? I'm just picking one. I could have gone either side. Actually, I guess I picked the minor of the two possible resonance forms because it would be more stable, less induction on the ketone rather than the ester. I could show both of them. I don't need to. You can stop here if you want to. I'll show you the formation of the other ester. Sorry, the other enolate. So what do I need to do? How can I get my product? I have just run a reaction that formed a beta keto ester that was 10 billion times more acidic than my starting material. And because of that, I just lost the product that I wanted because it fell into this acid-base trap. This reaction does not favor the formation of the enolate, but once the enolate forms, it can react. This reaction favors the formation of the enolate. So once it forms, it's stuck here. I can't get my product back because it just got deprotonated. So we have to show an acid workup. We would have to neutralize the base, the catalyst, and we'd have to protonate the enolate. whichever resonance form you show, one major resonance form, the other major resonance form, or the minor resonance form where the alpha carbon holds the electrons, whatever you show, all attacks from the same place. Alpha carbon attacks an acid, and the carbonyls reform. What are you thinking?
So in this case, the alkene is a stronger base than the, what is that, O negative alkoxide?
Carbon is always a stronger base than oxygen. The way you phrased it, the alkene is a stronger base than the alkoxide. Well, the alkoxide doesn't exist. It's an enolate because it's an alkoxide bonded to an alkene. But none of these structures exist. They're all slight versions of where the electrons are delocalized. There's 1, 2, 3, 4, 5 atoms all conjugated in series. That gives me 5 molecular orbitals. And there is the highest occupied molecular orbital holds this lone pair. And that highest occupied molecular orbital is split across 3 atoms with nodes in between on the other 2. So this lone pair is held at the same time by both oxygens and the central carbon. And it's the oxygens that stabilize that charge and make it easy enough to form, but it's the carbon that destabilizes that charge and makes it likely to react. So the carbon is the base, yes, because carbon is less electronegative, more likely to share its electrons. Carbon is a better base than the oxygen. But don't think that the carbon is not negatively charged as well. If I could, I think I'd actually show that step happening as that looks like such a silly little face. Delocalized across all 5 atoms and acting as a base, which atom is likely to actually use the electrons? It's the carbon. But you can't tell that from there either. Yeah. Cool. Fun, right? So on the final exam, you will have either a Claisen condensation where you'll be required to show that last additional acid workup step, or you'll show an Aldol condensation. Both the same number of steps. So I think in the past I've even given you the choice between an Aldol condensation or a Claisen condensation. You have to do one of them. Okay, questions on the mechanism? Makes sense? You understand why we form the product and then have to undo the product and then go back to the product? It's another thing that I lost points for when I was in OChem 2. And I fought. I said, I made the product. I don't know why I should have to show anything else. So now I torture you with my understanding. 10 billion times more acidic. How fun is that? All right.
You should be Dr. Evil for Halloween.
Oh, I get it. Yeah. A little rude. Just because I'm bald.
No, because you're like 10 billion times more acidic.
10 billion times more acidic. God, don't ever take me seriously. Lily?
On the acid workup step, that pi bond, like, I don't really understand that step.
So carbon is attacking
Okay.
and becoming protonated.
So that's attaching, like, is that forming a bond?
Always. Yep. From this pi bond to this atom, that's formation of a bond. But is it the atom on the left or the atom on the right? Which carbon of the alkene is actually attacking? It is the left. But sometimes it's hard to know because I start at a pi bond and I can't clarify which atom is using the electrons and which one is losing them. But notice from this resonance form, I needed to reform this carbonyl as well. So that carbon stays satisfied. So it is the alpha carbon that's attacking. But I could show it from this resonance form, alpha carbon attacking. I could show it from this resonance form. Carbonyl reforms, alpha carbon would attack. Any of the 3 resonance forms for this enolate are fair game. And I'll only anticipate you needing to draw one resonance form. When I write instructions for mechanisms problems, I usually try to say something like show all major resonance forms. For this, I would say something like you only need to show one resonance form of the intermediates. Maybe you like the negatively charged alpha carbon resonance form because it tells you where your nucleophile it is. That came off wrong. It tells you where your nucleophile is. It tells you where your acid workup needs to happen. Maybe you like the major resonance forms because it scratches an itch like it does in my brain. But for this mechanism, I understand these being more challenging resonance forms to use. I understand the alpha carbon holding the negative charge as an easier mechanism to use, or easier to use in the mechanism. It shortens the number of arrows you need to show, but it also clarifies why the alpha carbon is the nucleophile. It's not the major resonance form, but it is much harder to understand it otherwise. It can be. Ella?
Are we able to put, like, because you said acid workup, are we able to put it stepwise, like over the overall reaction, like 1 MEO minus and then 2, like HCl plus?
So we didn't do that, actually. We need to. Thanks for bringing that up. Yeah, so we said first catalytic base, but we do need to add second an acid workup is required, or you will not get your desired product. Aldol condensation, not true. We don't need to do an acid workup to get the aldol condensation product.
On the exam, are we going to have to do 2 arrow pushing mechanisms?
2 mechanisms, one from unit 4.
Okay.
So either acetal formation or acetal hydrolysis, or esterification or ester hydrolysis, and then one from unit 5, aldol condensation or Claisen condensation.
But we won't have to do any from before the midterm.
You won't have to push arrows pre-midterm.
Okay.
And actually the only mechanisms you had to show pre-midterm were OCHEM 1 mechanisms, halogenation, HX addition, acid catalyzed hydration, and halo ether, halohydrin. SN1, SN2, E1, and E2. You're right. So those were the ones from OCHEM 1 that you needed to be able to show for the homeworks. I'm not sure that I required it on the exam, though.
Was there a SNAR one?
And then the NAS and EAS, SNAR. That was the only one you needed to show on the midterm. There might be questions about that mechanism in the multiple choice, but it won't be in the arrow pushing part. 2 mechanisms, a roadmap, a synthesis, and multiple choice. 2 hours. And it's less than 2 weeks away.
What?
No, it's not. It's less than 3 weeks away.
Thank you. I was about to die.
Sorry. It's not roughly twice as long. It's more like a third longer. Midterm, I think, had a total of 30 some questions, and the final will have a total of 50 some questions.
I feel like we were rushing through the midterm.
Well, now you know, if you felt like you were rushing on the midterm, now you know how to prepare for the final, right? Or you know what to expect on the final. How many of you have done your your midterm analysis?
Doing it tomorrow.
Yeah. Do you know I didn't upload the final exam for my my OCHEM 1 class either? I didn't upload it for you guys until just recently, and I didn't upload it for the OCHEM 1 class. I really dropped the ball on it. I don't know. No, I went to show them, and it wasn't there. Okay, I had 36 questions on the final last semester.
Oh.
And
You're like,
So do
this
that again.
semester we're doing
So
50.
do that again, please. Do that again, please.
yeah, I do generally like just substitute the questions. So when you take that practice final, it will be very similar. 23 questions on your midterm, 36 questions on the final.
Only 23?
Mm-hmm.
I feel like there was like 100.
Okay, you had 14, 15, 16, 17, 17 multiple choice. And then the rest, what is the rest? 8, 6, short answer.
Multiple choice on an OCHEM exam is a joke. Like,
I'm not saying it's easy. And you had to do a roadmap problem. That was one question. It had 8 parts to it. So you could call that 8 more questions. That brings you up to 31. And you're right, the multiple choice is like, which of these 4-step syntheses doesn't work?
yeah.
Well, now I need to go through 4 steps 4 times and figure out where they all fail before I can prove that one of them works. I understand. I actually stumbled across one of our other professors' OCHEM 2 finals. He doesn't teach the lectures much anymore, but he used to give, I think, the same exam. 50 multiple choice, and then, Milena saw it actually, 50 multiple choice, and then, was it 20 short answer?
Here?
Yes.
20?
It was a beast. And those multiple choice questions were like, in words, show how to synthesize, or which route correctly synthesizes ethyl acetoacetate from ethanol. Right? Fun. I took some inspiration for sure. Actually, ethyl acetoacetate from ethanol is very easy, and I'll show you guys how to do it on the back sheet of this. We have Claisen addition to do, crossed Claisen, intramolecular Claisen, which is called Deichmann for whatever reason. But you know what to expect. Claisen reactions form beta carbonyl esters. So you could do that second sheet. But you'll notice on that second sheet, I've also got retrosynthesis. I want you to show how different crossed condensation products form. So aldol, ketones and aldehydes. Claisen, esters. But what happens when you have esters and aldehydes and ketones? Nobody named it. So I will just refer to them as crossed condensation. Not necessarily Claisen, not necessarily aldol. Then, also next week, we have Michael addition and Robinson annulation. Robinson annulation is a Michael addition followed by an intramolecular aldol. That guy really got off easy. He stole 2 reactions that already had names and named them after himself combined. Michael and Robinson, and that's the end. So take it easy this weekend, because next weekend you'll have a unit test. Do your homework, keep prepping, keep reviewing old material. I know it's hard when this stuff doesn't click right away, but you've got to go back and remember aromaticity and hybridization and esters and ethers, and keep reviewing, sprinkle in old material as you're working on new material.